Hey everyone, welcome. Today, we're going to break down the three simple rules that govern how absolutely everything moves, from planets in orbit to the phone in your hand. And trust me, this isn't going to be some dry physics lesson. This is the secret story of motion itself. So, let's jump right in.
So, let's start with the simplest thing imaginable, a ball. Just sitting there. It seems so ridiculously obvious, we never even bother to ask, why? Why isn't it moving? Answering that one little question, believe it or not, is the key to unlocking the entire universe of motion.
And that question, it leads us straight to the very first rule in our story. We're calling it the law of laziness, but you probably know it as Newton's first law. Yeah, I know, the law of laziness sounds a little silly, but honestly, it is the most perfect way to think about this big idea.
So, the big concept here is something called inertia. Basically, everything in the universe has this built-in resistance to changing whatever it's already doing. If it's standing still, it wants to stay still. If it's moving, it wants to keep moving just like that. You can really just think of it as cosmic laziness.
Okay, so what makes something more lazy than something else? It all comes down to its mass. The more mass something has, the more inertia it has. That's why it's a whole lot harder to get a bowling ball moving from a dead stop than it is a tennis ball, right? The bowling ball has way more mass, so it fights you a lot harder.
All right, so if everything is kind of fundamentally lazy and just wants to keep doing what it's doing, how does anything ever, change? How do you get something to start moving or stop moving or make a turn? Well, that brings us to rule number 2.
Well, you got to give it a push or a pull. And in the world of physics, that's what we call a force. A force is the one thing in the universe that can actually overcome an object's inertia and change its motion. So in the story of our little ball, the kick, that's the force. That's the moment that changes the game.
And this whole relationship is summed up in probably the most famous equation in all of physics, F equals ma. Force equals mass times acceleration. It's super simple, really. It just tells you exactly how much something's motion is going to change based on two things. How much stuff you're moving, that's the mass, and how hard you're pushing it, that's the force. It's that simple.
But, life's not usually that simple. What happens when you've got forces competing with each other? So look at this block. It's being pulled to the left with a force of 12 and to the right with a force of 2. What's going to happen? Which way does it go?
The secret is, it's the net force that matters, the overall winner of the tug-of-war. You just subtract the smaller force from the bigger one. So, 12 to the left, 2 to the right. You just subtract them. That leaves you with a net force of 10 pushing to the left, and that's the force that's actually going to make it move.
Okay, so that's the basics. But in the real world, things get a little more interesting. It's not always about a big obvious kick or a pull. See, there are all these invisible forces at play all the time, and we have to account for them if we want to understand what's really going on. Let's check back in with our little ball. If we kicked it in the vacuum of space, it would literally go on forever. But here on Earth, it eventually slows down and stops. Why? What's going on? Well, there's an invisible force fighting back. And here are the usual suspects, the big three invisible forces you're always dealing with. You've got gravity, which is always pulling down. You've got friction, which is always trying to slow things down. And then you've got something called the normal force, which is just a fancy way of saying the ground pushing back up so things don't fall through it.
So, with all this pushing and pulling happening from all directions, how on earth do you keep track of it all? Well, physicists have this awesome little tool called a free body diagram. It's basically a simple map that lets us see every single force acting on one object all at once. Let me show you what I mean. On the left, there's our ball rolling up a ramp in the real world. And on the right, that's the free body diagram. We've taken all those real, messy, invisible forces, gravity, the ramp pushing back, friction, and turned them into a clean little diagram that we can actually work with. All right, we're on to our third and final law. And this one's a real mind-bender. It reveals something pretty profound about the universe. It turns out no force ever acts alone. Every single interaction is a two-way street. I bet you've all heard this a million times. For every action, there is an equal and opposite reaction. What that really means is you literally cannot push on anything without it pushing back on you with the exact same strength. The key takeaway here is that forces always, and I mean always, come in pairs. Okay, but this is where a lot of people get tripped up. Let's test this out. You've got a book just sitting on a table. Gravity is pulling the book down, the table is pushing the book up. Seems like a perfect action-reaction pair, right?
I mean, they're equal, they're opposite. What else could they be?
Nope. And this is the part you absolutely have to remember. A true action-reaction pair acts on two different objects. So the Earth pulls on the book. That's gravity. The reaction to that is the book pulling on the Earth. The table pushes on the book. That's one force. Its partner is the book pushing down on the table. It's always an interaction between two different things.
Okay, it's time to put it all together. All three laws working in harmony to solve a puzzle you've definitely experienced but probably never thought about in this way. The elevator problem.
I mean, you know that feeling, right? The elevator doors close, starts to go up, and for a split second you feel heavier, like you're being pushed into the floor. Or it goes down, and you get that little lurch in your stomach. That is not just in your head. That is pure physics. That is Newton's laws talking to you.
So think about it. When the elevator starts going up, it has to accelerate you. The floor has to push on your feet, not just enough to hold you up, but with an extra little shove to overcome your inertia. That extra push from the floor, that extra normal force is what your body registers as feeling heavier.
And, you guessed it, the exact opposite happens when you accelerate down. The floor doesn't have to work as hard to hold you up because gravity is already helping you move down. So the floor eases up a bit, the normal force on your feet gets smaller, and for a moment, you feel lighter. It's the perfect showcase of all three laws working together.
All right, you've made it this far. Time for one last brain teaser to see if you've got it. We've got three identical sealed jars on scales. Jar C has one firefly just resting on the bottom, Jar B has one firefly hovering in the middle, and Jar A has three fireflies hovering. So how would you rank them from heaviest to lightest? Seriously, pause and think about this one. What's your gut feeling? Ready for this? The incredible answer is Jar B and Jar C weigh exactly the same, and Jar A is the heaviest. How is that possible? Well, for a fly to hover, its tiny wings have to push air down with a force exactly equal to its own weight. That downward force of the air presses on the bottom of the jar just as much as the fly's body would. So one hovering fly weighs the same as one resting fly. And that right there is the magic of these laws. They show you the hidden rules behind everything, which kind of makes you wonder what invisible dance of forces is holding your world together right this very second.